Pasito, quiero respirar tu cuello despacito. Deja que te diga cosas al oído.
Hello guys, so today we are going to start GOC, that is General Organic Chemistry. This chapter basically deals with the different prerequisites one needs to understand the different phenomena and gaining an overall view of the different organic reactions and species. GOC means General Organic Chemistry. This is the basic for foundation you require to start gaining an in-depth knowledge of organic chemistry. So there are different parts in which we can divide GOC. The first one being nomenclature. Second is the isomerism. Third one is the substrates, reagents, governing factors, for different species, behavior, and organic chemical reactions. Fourth one is the types of organic reactions. And overview. We will not get into the details of these organic reactions now because we will deal with them in later chapters. And fifth one is the last one, that is practical organic chemistry. This practical organic chemistry POC basically includes the qualitative and quantitative analysis of different organic compounds and how to measure them quantitatively, and the tests you will perform in laboratories, all those are included within this POC. So guys, we are going to start isomerism. Isomerism arises when two compounds having same molecular formula have different structural or spatial arrangements in space. So arrangements or different spatial arrangements. Spatial means within space. Spatial arrangements, different arrangements within the space. So we can divide isomerism basically into two parts. One is the structural isomerism, another is the stereoisomerism. So this stereoisomerism mainly depends on this spatial arrangement, different spatial arrangements of two molecules, and the structural isomerism depends on the structure of the molecule. So structural isomerism can be of many types. The first one being chain isomerism, then tautomerism, then we have positional isomerism, then we have functional isomerism, then we have ring chain isomerism, and at last metamerism. So let's start with the structural isomerism part. So we are going to start the first of structural isomerism, that is chain isomerism. First we write structural isomerism. So we are going to start chain isomerism. It is the type of isomerism that is resulted due to variation in the carbon chain or carbon skeleton, but ultimately results in the same molecular formula. You will better understand this when I give an example. So it results due to variation, that is, it can be branched or straight. Based on that, this isomerism appears. Variation in the carbon skeleton or chain, but resulting in the same molecular formula. So let's take an example. Let's take C4H10. So we draw the line projection, line angle projection. This is the line angle projection for C4H10. We can draw this, or we can draw this one. So the formula for both are C4H10, but see here the principal chain contains 4 carbon, 4 CPC, that is 4 carbon principal chain, and here the principal chain contains 3 carbon. You can take this or this, both are equivalent. So 3 CPC plus 1 methyl group. So as I said, variation in the, it appears due to the variation in the carbon skeleton, but has the same molecular formula. Both are C4H10, but here it is a 4-membered carbon skeleton and with no substituents, but here it is 3-membered carbon skeleton with a methyl group, and these are isomer, these are chain isomers of each other. You can also take other examples like C5H10, C5H12, so it can be 5 CPC. If you degenerate the principal chain step by step, that is, you take, here it is 5, so you take 5, then you take 4, then you take 3. If you do like this, then it is easier to draw the isomers, otherwise it becomes difficult. So 5 CPC, that means it will be straight chain. This is the line angle projection lap for pentane. Then it can be 4 CPC 4 CPC plus 1 substituent, that is methyl. You can place it here or you can place it here. Now see, this one is, if you number the carbons, this one is 1 2 3 4. If you again number it, then this is 1 2 3 4. This 2 position is equivalent to 3rd position. So if you can place the substituent here or you can place it here, but both are equivalent to each other. So we get only one 4 CPC and 1 substituent isomer. So this one is 4 CPC 1 substituent isomer. Then we will have 3 CPC, 2 substituent, 2 methyl, or 1 substituent, 1 ethyl, because 3 CPC 3 and 2 5, here also 3 and 2 5, this one C5. So we will get like this: 3 CPC, 2 methyl, here 1, here 1. So this becomes 3 CPC, 2 methyl. Now if you try to draw this one, with 1 ethyl group, 3 CPC, 3 CPC with 1 ethyl. Then you can see that this one is equivalent to this one, because when you number the principal chain, then it will go around this, like this. Now this becomes the principal chain, so this cannot be the case, so this one is wrong. So again we get one isomer only from 3 CPC and 2 substituent methyl group. Isomerism. It is the type of isomerism that arises due to variation in the position of different functional groups or substituent atoms related to the main chain or unsaturations, but at last the molecular formula as previously always remains same. So it is the type of isomerism so it is the type of isomerism that arises due to variation in the position of unsaturations functional groups or substituents similar, let's write same or identical, such that the molecular formula remains same. So let's take an example. Let's take C4H8. The double bond can be here or it can be in the terminal carbons here. So these two are positional isomers of each other. Let's number it 1, it 2, and let this be 3. Now you can see that these two are positional isomers of each other, because the molecular formula remains same in all the 3 though, but here you can see the position of the unsaturation changes from the middle 2 carbons to the terminal ones, and here you can see that both chain isomerism plus positional isomerism takes place. See, if this carbon was present here, we have simply shifted one carbon from the principal chain to a substituent methyl group, so we are getting a chain isomer, and at the same time we are shifting the position of the double bond. So this, from this if we see, then here both chain isomerism and positional isomerism takes place. So we call this type of isomers structural isomers. Whenever there is a combination of 2 types of structural isomers, we call them directly structural isomers. Suppose there were metamerism as well as positional isomerism, then we will call that one, since both are present, structural isomers. Any combination of 2 are designated as structural isomers. So 1 and 2 are positional isomers, 2 and 3 are also structural isomers. 2 and 3 are also structural isomers, and 1 and 3 are also structural isomers. Let's take a few more examples. C4H9OH butanol. So this should be like this, it can be this, or it can be this. Someone would like to place it here instead of here, but as I told previously in chain isomerism, these 2 places are equivalent, because if we count from this side, it becomes 2 and this becomes 3, and if we count from this side, examples like cresols show positional isomerism. So cresol is basically a benzene ring with 2 methyl groups as substituents. So this is orthocresol, O-cresol. So we are seeing the substituents playing the leading role as for positional isomerism in this case. Previously we saw how the functional group is playing the leading role, and previous to that we saw the unsaturations are causing the positional isomerism. Now this is due to the substituent, different position of the substituents. Next is metacresol, M-cresol. Then we have at last the paracresol or peak cresol. So as you can see, they are all identical in molecular formula, but the relative position of the methyl groups are different in all the three. So 1, 2 and 3 are positional isomers of each other. So guys, we are going to start functional isomerism. So guys, we are going to start functional isomerism. So what is functional isomerism? Functional isomerism is resulted due to variation in the functional groups present in two different structures having the same molecular formula. So it is due to the presence of two different functional groups, aldehydes and ketones, carboxylic acids and esters, and cyanides and isocyanides. Also sometimes aldehydes and unsaturated alcohols also show functional isomerism. So let's take an example. C4H9OH. So one is the alcohol containing structure, another will be ether. If you check carefully, the molecular formula for this is C4H9OH, as well as this is C4H9OH, or you can say C4H10O. So this is C4H10O, as well as this is C4H10O. So these two are functional isomers of each other. So as we are speaking, C4H9OH and C2H5OC2H5, this one being alcohol and this one being ether. So if we draw the structures, this is the ether and this is the alcohol. Also you can have this one or this one or this one. So these all are possible. I'm just giving examples to show the relation between them. Some more may be possible. So 1 and 2 are functional isomers of each other. So 2 and 3 or as we can see, a combination of positional isomers plus functional isomer. So as we told previously, whenever there is a combination of two types of isomers in structural isomers, we name them combinedly structural isomers. So this is a structural isomer. These two are structural isomers of each other. 1 and 3, as you have already guessed, is a positional isomer. Positional isomers. And 2 and 4, pretty simple, again positional isomers. And if you wanna compare 1, 2, 3 or 4 with 5, then we can see a combination of chain isomerism plus positional as well as functional. Positional for some and functional for some, but chain is, as you can see, there has been a branch, so chain isomerism has taken place and positional isomerism has also taken place if you consider 2 or 4, and functional isomerism plus chain isomerism has taken place if you consider 1 and 3 with 5. So it is also a case of structural isomerism. In case of aldehydes and ketones, you can have many examples. One of the simplest is between C2H5 CHO and CH3 COO CH3. As you can see, the molecular formula for both are same, but one is aldehyde, another is ketone. So this one is, so they are functional isomers. This one is propanol. This one is dimethyl. Ketone, or you can say propanone. Also, as I told you earlier, you can find functional isomerism in case of unsaturated alcohols. And aldehydes, such as example CH, 2 double bond CH, CH2H. And this one is the alcohol, unsaturated. Alcohol, and the other is the aldehyde, CH3 CH2CHO, propanol. Also, you can find functional isomerism in case of aromatic alcohols and phenols, like aromatic alcohols and phenol phenols. So benzene ring CH2OH with benzene ring CH3, or you can say the thing will be the same still, OH CH3. So these two are functional isomers of each other. So next we go on to metamerism. Metamerism is the type of structural isomerism that arises due to variation in the number of carbons on the both sides, or you can say around a polyvalent functional group. And as you can guess, polyvalent functional group definitely includes oxygen containing functional groups, or carbon containing or nitrogen containing functional groups. So you can have, so let's write the definition. So it arises due to variation in the number of carbons on both sides of a polyvalent functional group. So like functional isomerism, this also has many so you can find metamerism in ethers, because on both sides of the oxygen atom the number of carbons can be different according to the alkyl group present. So ethers, where oxygen is bivalent, it can take place in esters. Again a bivalent case. It can take place in ketones. Again bivalent in 2-degree amines. Three-degree amines. This is trivalent. And so these are the cases where you can find metamerism, and let's move on to the examples so that you can understand better. Let's take the examples. So you can have C4H10O, that is ether. It can be like this, that is 2:2, or it can be C3H7O CH3 1:3, or you can say 3:1. Both are equivalent. 3:1, 3 carbons here and 1 carbon here, so 3:1. 2 carbons here, 2 carbons here, so 2:2. Also you can see in case of 2-degree amines, C6H15 keep 1 carbon here, keep 1 carbon here and 5 carbons here, so I'm just writing the number of carbons. So C1 and this is C5, or you can take C2, C3, sorry, C4, then you can take C3, C3. So this is 2:4 or 4:2, this is 3:3, this is 1:5, 5:1. If you try to further increase the number of carbons on this side, it becomes identical in the reverse order with this and this. So you can also take 3-degree amines. Degree amines, C6H15, so H15N. So this can be C6, 2 carbons on 3 sides, and C2, C2, C2. C3, C2, can be N, C4, 1, 1, 1:1:4, 1:2:3, 2:2:2. So these are all examples of metamers, and with this we end the discussion for metamers. After this we will continue to tautomerism, which are very interesting, and we will discuss them with proper mechanisms. So guys, stay tuned for the next video, and like and subscribe our channel.
Yellow diamonds in the light, and we're standing so